Section 2.12.2 is simple regression. And simple regression is a analysis between two continuous variables. So in this case, we have one dependent variable. And this we're going to term that as y. That's the notation is going to be y, and that is called the response variable. Okay, this is the variable that we're trying to explain differences in. And then x is the predictor variable. So x, we're going to say that changes in x lead to changes in y. And this is going to be a linear model. But note that simple regression does not prove cause and effect. Okay, we might have a theory that tells us the changes in the predictor will lead to changes in the response variable, but it's difficult to prove cause and effect. Okay, so here's some examples of some estimated regression equations out of the textbook. In the first one, we've got sales of a company, okay, and that's equal to 268 plus 7.37 times the number of ads. Okay, so this is the outcome of a regression model, and the interpretation of this regression equation is that each additional 1 unit of advertising will lead to an increase in sales of 7.37. Okay, and here's another one. So the rent of a building is related positively to square footage of the building. So it says that each additional square foot adds $1.05 to the rent. Okay, and these models can also be used to make predictions. So if you take any value for advertising, in this case 10 million, and multiply that by 7.37, you get a prediction of advertising equal to about $342 million. Okay, so regression models can be very useful in terms of making forecasts or other types of predictions that a business firm might be interested in. So here's an example of an interpretation of a regression model and the prediction of what the value of the dependent variable would be, or the y variable, when the independent variable, or the x variable, is equal to a certain value. So part A asks, interpret the slope of the fitted regression. Home price equals 125,000 plus 150 times square feet. So first of all, you notice that we have a positive sign here. So as square feet increases, home price will also increase. So the interpretation would be that each additional square foot increases the home price by $150. And then the prediction, or what is the prediction for home price of square feet equals 2,000, what you do is you plug in 2,000 on the right-hand side of the equation, multiply that by 150. Okay, so that would be equal to 125,000 plus 300,000. And so the home price would be $425,000. Okay, so at this point, it's important to recognize that prediction outside the range of the data should be done cautiously. That means if you have a variable of square feet and the minimum is equal to 500, a 500 square foot home, and the maximum is equal to 5,000, predicting home price below 500 for a square foot house, a house that has square feet of below 500, and for a house that has square footage above 5,000, is probably going to be inaccurate. Okay, just because we don't have much information on houses that are in smaller houses or larger houses. Okay, so just be careful with those predictions. And in the extreme case, you can think about a house that has square footage of 0, and so 0 times 150 would be equal to $125,000. Okay, so that prediction is ridiculous. It's not something that you would want to do. So that's an extreme version of this caution. So here's another question from the chapter, number 12.8. Interpret the slope of the fitted regression, where sales is equal to $842 minus 37.5 times the price. So here we have a product that you have produced and are trying to sell, and this negative sign tells us that as the price goes up, sales, or the volume of your sales, goes down. Okay, so interpret that variable using the quantitative measures here, and then make a prediction for when price is equal to 0. What is a prediction for sales? And the printed version of these notes will have the answers. So in section 12.2, we just talked a little bit about simple regression models and what they can be used for, with some empirical examples. And in this section, we're going to talk about the regression models themselves. So first of all, some regression terminology. So the theoretical relationship for a regression model looks like this, with y is the dependent variable, and that's a function, going to be a function of x, which is the independent variable. And here we have these Greek letters beta. These are theoretical parameters, where beta 0, we're going to call that the intercept, and beta 1, we're going to call that the slope. And then epsilon is what we're going to call an error term. This error term is assumed to be independent. What's called independent, that means it's random. The error term, any one error term, and you'll have one for each data pair in your data. Any of those error terms are not going to depend on any other of the error terms. And we'll talk more about what that means when we start talking about violations of the independence assumption. When we specifically when we think about time series data in chapter 14. And the error term is assumed to be normally distributed. It has a symmetric distribution with a mean of 0 and then a constant variance, sigma squared. Okay, so these parameters, the theoretical parameters, are unknown. Okay, and again, the intercept is beta 0, and the slope is equal to the change in y divided by the change in x. And this is just the same slope that we all learned about in algebra class. Okay, so graphically, this is what an estimated regression model would look like. It has a linear relationship where the intercept is beta 0, and here the intercept is positive, and then the slope parameter, beta 1, is equal to the change in the variable on the y-axis, the vertical axis, divided by the change in the variable on the horizontal axis. Okay, and the slope is calculated like in algebra. Okay, and then the error term is going to have this normal distribution around the fitted line. Okay, so here's here's some examples of what some regression lines might look like. So this first line with a positive slope, beta 1 is greater than 0. This is similar to the regression line we just saw. And it's also possible that the fitted line is going to have a negative intercept, where the positively sloped line hits the vertical axis in the fourth quadrant, where the value of y is going to be negative. And a negative sloped regression model, regression equation with a negative slope is going to be downward sloping, going from the northwest portion of the first quadrant down to the southeast portion of the first quadrant. In this case, the intercept, the y-intercept, is going to be positive, and as x increases, y is going to decrease. Okay, and so that's the theoretical regression line. And what we're going to be doing is estimating what those unknown parameters are given our data. So the book talks about a fitted model, okay, or the actual regression model. Okay, the notation for that is going to be, we're going to use lowercase b's to replace the betas. Y hat is going to represent a predicted value of y. Okay, so once we estimate the regression line, we eliminate the error term, and for any value of x, we can predict values of y. And this is a similar thing that we did in section 12.2 of the textbook. Okay, this predicted value of y is considered the expected value of y given any value of x. Okay, and so once we have estimated a regression model, the error term, it's also known as, or the residual, which is also known as the error term, is equal to the observed value of the y variable minus its predicted value. And so these I subscripts tell us that every value in the data set, every pair of x and y, is going to have its own predicted value and its own error term. Okay, and these residuals, these individual residuals that have a mean of 0 are going to be what's used to estimate the standard deviation of the regression model. And here is kind of a crooked picture. I scanned this from my textbook, and that's why it's a little crooked, so apologies. So the red line here is the fitted regression line. Okay, it's plotted with x on the vertical axis and y on the, x on the horizontal axis and y on the vertical axis. The scatter plot that we talked about in section 1 is represented by these blue squares. Okay, so the residual, E sub I, is the difference between the actual value of y at an actual value of x minus the predicted value, which is found on the red line. Okay, so in this case, y sub I is greater than the predicted y, and so the residuals will be positive. Okay, so for residuals below the red line, these values are